As we talk about solutions, we bring up ideas such as intermolecular forces and the impact they have on solution formation, and that we have to have attraction between our solute and our solvent particles. We've also brought up energy associations, so enthalpy and entropy, and how they could impact solution formation. There are a couple of other factors that are going to impact solution formation that we'll talk about in this video. So our intermolecular forces determine whether or not a solution can form. If we have a strong enough attraction, our solution can form. But we also talk about solubility in terms of how much solute can dissolve in a particular solvent. And this can be impacted by temperature or pressure. Now, when it comes to temperature, the impact temperature has depends on the phase, and that's the phase of the solute. So if we have a solid solute, for most solids, solubility increases with increasing temperature. And so we've got this graph here showing some common ionic solids and how their solubilities increase with increasing temperature. Now, how much we're going to see that variation is going to be dependent on our thermodynamics and our intermolecular forces. We do see one example or one exception. We see that sodium sulfate, it actually decreases. Again, that's going to be tied back to that thermodynamics. Now, if our solute is a gas, for most gases, the solubility actually decreases with increasing temperature. So notice in our picture here, we're comparing cold soda to warm soda. The warm soda has all that fizz. That is now undissolved carbon dioxide, versus the cold soda where we have little fizz. That means most of our carbon dioxide is staying dissolved. The other factor that's going to impact solubility is going to be pressure. Now, pressure impacts solubility of gases only. The solubility of a gas in a liquid is directly proportional to the partial pressure of the gas above the liquid. So if I have a liquid, that liquid can evaporate. That liquid will be in equilibrium with gas above it that has evaporated, and that gas above it's creating a partial pressure. As the partial pressure above the liquid increases, solubility increases. Carbon dioxide is a good example. Carbon dioxide is not particularly soluble in water. It's a very weak solubility. In our first image here, we can see small amounts of carbon dioxide dissolved, and we've got a large amount of gas above the solution. Now, we increase the pressure here by decreasing the volume. So here we're using a piston to decrease the volume, which increases the pressure. That forces gas particles into solution, and those gas particles can't escape because it requires too much energy to push that pressure back up. So gas particles will dissolve back in that solution until we reestablish an equilibrium. So looking at our problems, we want to think about why we see some of the things we just talked about. So why do we think increasing the temperature is going to increase a solid solubility? So we go back to those things we said that we're going to determine if a solution dissolves or not. It's going to be those intermolecular forces. When we talked about phases, we said we could heat solution or substances to break their intermolecular forces, which would cause them to change phase. They're going to also impact solubility. Increasing the temperature provides more energy to our particles. If my particles have more energy, that gives them a better ability to break those intermolecular forces. And so if we can break our forces better, then our solute is going to be able to dissolve more easily. So again, we get that better ability to break attractions. So that will always be true if we have or mostly true when we have a solid. We have more energy, gives us a better ability to break those intermolecular forces. Now our gases are going to be the opposite. So we have our soda example again. It's very common that we're going to keep sodas cold. So we have an example here, pouring a cold soda versus a warm soda. The warm soda has a lot of fizz. That's indicating a lot of carbon dioxide leaving that solution. Whereas the cold soda, we have very minimal fizz, so less carbon dioxide leaving. That's because the carbon dioxide is more soluble in the cold solution than it is in the warm solution. And again, that goes back to those intermolecular forces. If I have a solution let's say I've got water. Now, to form the surface of that liquid, we're going to have a whole bunch of water molecules connected or attracted to one another, creating a surface tension. And then under that, we would have our carbon dioxides. Now, carbon dioxide, in order to get out of that solution, has to break through the attractions, causing that surface. Now, generally for a gas, because the gas isn't necessarily going to be particularly attracted to the water to begin with, it can easily escape. But the higher the temperature, increases the ability to, again, break attractions. But this time, breaking those attractions not only spreads it out through the solution, but it actually causes it to break through the surface. And being a gas and being lightweight, it's going to be able to do that and move above the solution. So higher temperatures actually allow our gas particles to escape. And then finally, we're asked, what do we think, or why do we think a soda bottle fizzes when we open it? Which causes the pressure inside to decrease. So if we look at any bottle of soda or can of soda, it'll have a warning that it's bottled under pressure. Now, we use that pressure to actually force carbon dioxide to dissolve in the water. It's not very soluble. But once we open that container, that allows a pathway for our gas to escape. It increases our volume, it decreases pressure. If we're decreasing the pressure above the solution, remember that we said our solubility is going to decrease. If we had high pressure, it's hard for my particles to push against that pressure. They don't have anywhere to go. They stay pushed into that solution. If we decrease the pressure, they can now escape more easily. So if we've got a bottle of soda, we want to keep it cold and we want to keep it sealed to keep as much carbon dioxide dissolved as possible. If we leave it sitting out where it can get warm, we leave the lid off, the carbon dioxide is going to escape and that soda is going to go flat. So we've talked about a good number of things in regards to solutions. We talked about intermolecular forces and determining how they're going to interact to form a solution, what types of forces we have present. We've talked about entropy and enthalpy associated with solution formation. We have described concentrations of solutions. We've looked at colligative properties. We've looked at types of solutions in terms of saturated, unsaturated, and supersaturated. And we've discussed impacts of temperature and pressure.